So I welcome you again, everyone. Thank you for coming. And now we can start with the presentation. That's a beautiful GIF, I think. So today's topic is small but mighty engineering the CubeSat framework. So this is me, I'm Tomáš, I welcome you again, and I'm the structure lead of the student team YSpace, and I'm the engineering student in BUT. Right now, what I'm working on in the structure team, I design, develop, and I do technical documentation, and trying to lead the team, yeah. Right now, I'm working as a research and development engineer in Litigo Space, which is focused on development and production of analytical instruments. In the free time, I'm a member of amateur theater, Papeto. If you would like, you can Google it and come sometimes. And to have enough points on this slide, I'm a retired tennis player from my town. So today's agenda. We will start with some introduction to CubeSats. Second will be key components, standardization, then there is a beer break to don't get you bored enough. Then there are challenges in miniaturization, space challenges, simulations and testing, another beer break. And I want to welcome our guests that will be today presenting their topics too. And it is Mr. Roman Dohnal and Mr. Josef Pouzar. Thank you for coming. So we will start. What is the CubeSat? It's a small sized satellite. It's 10 times 10 times 10 centimeters. It's a cube. It has a low weight and standardized design. What is good? Just try to imagine a big Rubik's cube that have 10 times 10 centimeters. And here I have for a little comparison, there on the next slides, there will be more, some comparison in sizes to try to imagine how big these satellites are. We can start with large satellite. It can be 1 ton by mass, and we are like down here. CubeSats are called nanosatellites, and don't get misguided. There can be even smaller satellites. What do we mean by standardized design? As you can see here on this picture, maximum of 24 units. When you see this, like 1U, it's called, and that U stands for 1 unit. You can stack them. It's perfect for like fast development and everything, and it's easier to make the satellite by this way. And it depends on your mission, what you want to do, and you can, if you remember that with Rubik's cubes, you can stack them on together. Just imagine it like building a Lego bricks or something. And you can go from 1U to 2U, 3U, 6U, and I think maximum today is 24U. Who is familiar with Star Wars? Perfect, that's a good crowd. For comparison, as I said, I have here a comparison of CubeSats to AT-RT Walker, which was used in 7th Division in Clone Wars by the clones, but I know that's a basic knowledge. So why we want to use CubeSats? Low cost, rapid development. It's like two perfect things, and it's hand by educational opportunities. Nowadays, the CubeSats are used mainly in student and education like development. It's perfect opportunities for students to get hands-on. How is it developed? How to behave in like space industry, etc. Then we have, of course, scientific research, and I love this GIF, technological demonstration. So, some key components of CubeSat. We have structure, and then we have EPS, COMS, ADCS, OBC, and PLD. I hope everyone is familiar with those shortcuts. If no, I was prepared for that. When we are starting with shortcuts, in the space industry, they love to use shortcuts or acronyms. So EPS is electric power system, COMS are communication systems, ADCS, altitude determination and control system, OBC onboard computer, and PLD payload. Here I took a picture. This is from NASA sites. They have like this nice table of acronyms in space industry, and don't be fooled, this is just a fraction of their power, because they have a whole alphabet, and I didn't like, this is not full A, it's more longer. So yeah, they have acronym for everything, I think. And now we are coming to the first beer game. Please, Klarka. Yeah, perfect. So OSIRIS-REx. OSIRIS-REx is a mission that successfully concluded its primary objective in year 2023, when it came back to Earth with a sample of Bennu asteroid. Pretty nice mission, and today beer's game is, it's pretty hard, so it's for 10 beers, okay? What is the acronym of OSIRIS-REx? No one? Okay, I will say it then, because it's for 10 beers, so I will not take longer. Its origin, spectral interpretation, resource identification, security, regulate, explorer. Yeah, as I said, space industry love acronyms. Okay, we are continuing with key components. So, as you can see on this picture, this is our project, which should fly in 2025. This is called Kostka. And here are, like, you can see the subsystems by the color, and you can see that one subsystem is missing. It's ADCS, Altitude Determination Control System, and we didn't use it in our CubeSat. It don't need to be there, but it's like part of the mechanical engineering, so I will, for a short time, talk about it. We can have active ADCS and passive ADCS. In active ADCS, we have sensors, actuators, and some other stuff, like it can be OBCs that are like communicating with the sensors and actuators. Under sensors, there are sun sensor, star trackers, gyroscopes. Just to say something about it, star trackers is just the device that see the stars, and it can calculate the position of the CubeSat depending on what it sees. Actuators, reaction wheels, magnetorquers. Reaction wheels, like, I hope everyone is familiar with that. It's dependent on Newton's third law, action and reaction, and it's for, actuators are for moving with the satellite if we want to, like, position them or on something, if you have camera or anything. Then there is passive ADCS, gravity gradient stabilization. When we talk about passive ADCS, it mainly depends on gravity and magnetic poles of the Earth, magnetic field, sorry. And it can be like through the structure itself. It should be somehow like ferromagnetic, and the gravity of the Earth will move with the satellite on its own way. So yeah, but we know that Earth magnetic field is not homogeneous. So it's not like good for satellites. We want to make a precise position for them, because it will move like here. It will move different heat. It will be in on different position to the sun or anything. So yeah, and spin stabilization, it's totally passive. When you deploy the CubeSat out to Cosmos, it will spin randomly. These spins are stabilizing over the time, that it will spin really, really slow without using any devices to it. And it can be like powered up by axis symmetry on the satellite. So now we will talk about structure itself. A complex task disguised as simple one. When I ask you if you will make me the cube about 10 times 10 times 10 centimeters, you will say to yourself, well, that could be easy. Yeah, it is easy, but there are some problems to it. Always there are problems to it. So about framework itself, it needs to be compact and modular. It's the best thing for like future development if you are working in some team, because you want to replace, maybe you want to replace some payload or anything, if you need to plan B or anything. So to don't recreate the whole satellite. Then low weight, you must look at right materials, height strength, electromagnetic compatibility, also called as EMC. You need the materials, or okay, start again. EMC is something that like you don't want to interrupt anything in your satellite, and everything interrupting everything. You can have a structure that can interrupt the things you have inside, and you don't want that. So choosing right materials or location of the components that you don't want to interrupt in that term. Then we have thermal, internal heat dissipation, temperature gradients, heat pathways. Yeah, in the vacuum, there's nowhere where can heat go out. So we have heat pathways and internal dissipation. Satellite can be, it's fascinating, but it can boil on the orbit if you don't make it right. So yeah, requirements, compatibility. Here again is a picture from our project. Also, it's still the Kostka. And as you can see, some main parts like top, middle, and bottom frame, and rail side. Frames are used to connect the both sides of the rails, and then there are threaded rods. Threaded rods, they are used to mount the PCBs, which are power circuit boards, where are all the subsystems in the CubeSat, and we want them like have good mounted in satellite. So technical documentation. As I like to say it, translation into mechanical engineering language. We need everyone to understand what we are doing, and this sometimes we can like come up with some mistakes we made during the modeling. So yeah, technical documentation is pretty big part in these situations. Of course, verification that all requirements have been met. It's due to on the model, maybe in some CAD programs you can, but it's best always in these years still on the paper. Of course, you have PDF or something in computer, but not counting on that. And some tolerances, as you can see here. So it's pretty simple part, but still it's like hard technical documentation to get everything to position and meet all the requirements you've got from the institutes you work for. What is good? Technical documentation works on almost every subsystems. Always you need to know what you are mounting, what you need, and you need the dimensions of that. So if you don't have step file or anything. So this is the technical documentation of PCB. As you can see, the mounting holes here, they are like on the different position in every corner. It's a little bit of pain when it comes to technical documentation, but it's necessary because there is always one way how to mount the PCBs in your CubeSat, which is perfect. But, sorry, fun fact. I'm saying fun fact because no one gets hurt in these fun facts. I have a few of them in my presentations. So this fun fact is about Russian rocket Proton-M that crashed less than a minute after its liftoff. Maybe someone is familiar with that, but it was a human error. Some mechanical engineer which was mounting the gyroscopes and altitude determination control system in this rocket, he had those holes and he couldn't fit them right. And he was thinking to himself, oh my God, someone missed the right spot. So he took the drill and drilled the PCB. Of course it was working, but all the subsystems were upside down. So the rocket thought that space is underground of the Earth. So it made this beautiful maneuver, which wasn't constructed for, and ended like this. So we will continue with CubeSat deployers. Its mechanisms that release the CubeSats from larger spacecraft, such as rockets or ISS, International Space Station. Still, you can see all the acronyms for everything. So GM, Japanese experimental module, there are mounted these two deployers. JSSOD, Small Satellite Orbital Deployer. It's first of its kind, and it's used today, such as NRC-SD, NanoRec CubeSat deployer, and some details you can see here on this overview. Here you see GEM overview, the whole module on the ISS, and here you can see its airlock slide table. This red part is the deployer. Exactly this one, NRC-SD. And this is a picture of deployment of 3 CubeSats. So NRC-SD mechanical interface. This is technical documentation in the requirements. You always need to fit your CubeSats to the things. They will be mounted in the rocket or anything. So yeah, you can see some dimensions for it, but this is pretty simple one. It's just like main dimensions. And this is taking me to standardization. Some answers already exist. Yeah, standards are, like the last sentence, keeping us from getting a little bit crazy on our development. So yeah, and it reduces time and cost. Time equals cost. And accelerate development. As you can see on this simple picture, yeah, standards are used to push you in your knowledge, even if you didn't work with that thing before. We have European Cooperation for Space Standardization. If you work with ESA or any space agency in Europe, you will definitely look up those. They have really so many standards. Almost everything is standardized. Yeah, they were pretty quick with that, or quick, sorry for that. As you can see on the left, in Z-axis for CubeSats, that is standardized, maximum mass, and all the other axes. Even the rails you can see here, they have standardization for all the dimensions, because you can on few sides you can like overcome the dimensions of Rails, but Rails must always be on its place due to deployers. Did you catch something like interesting on one of those pictures? No? Okay. This optional TunaCan. You can stack you can stack TunaCan on your CubeSat. Of course you can, but that wouldn't be too good for the mission. But TunaCan is like used acronym for everything that is shaped like TunaCan. There are right now they are working on a propulsion system that is called TunaCan, and yeah, it's just because of these dimensions, 36 millimeters max, which is like average height of TunaCan, and it's just someone said it and it catched up in space industry. So you can if you have money. So something for ECSS. This is only one document from the European standards, and it's only its table of contents. How you can see, it have a lot of slides. Sorry, lists. But as I said, it's only one document. So if we coming up, that's how it's called, structural general requirements. We can still go up. Then there is E30 discipline, mechanical engineering, and we are here. Only one document, all of this branch. We still can go up. Space engineering branch, and that whole tree, we are only here. That was before that was that mechanical engineering. Still we can go up. So, and this is like a main branch right now. So system description, it's called ECSS disciplines. And yeah, if you want to work anything space related, you will definitely like hit those. And now, thank you for your attention, and we have beer time right now. So enjoy your beer, and we will start about 15 minutes. Okay, so we will continue with the presentation. So now it's the topic challenges in miniaturizing. I hope I said it right. So main challenge, limited space. Where put all these things we've got from the other subsystems? As a structure team, we always get like all those PCBs, those beautiful green things or other colors, and they are like throw it on one horde and say, okay, we need it in the satellite, but you have only space 10 times 10 centimeters. So now you're asking yourself, how? That's a good part. But we have there those requirements and standards, so there is times where it will get easier, and we need the system engineering to tell everyone that it's not possible to like get it inside there. Other challenges: resistance to space environment, temperature changes, outgassing, and cosmic rays. Here are another comparison just for the limited space. Like we are somewhere here and here, and you can see, like, let's say classic satellites, large satellites. You have enough space to fit so many things into it, but there is a challenge with the CubeSats, with the education and everything, and get hands on it. So, yeah. Vibrations and shocks. So the vibration sources are rocket launch, deployment mechanisms, and orbital maneuvers. When we are talking about vibrations, they are like really dangerous for our structure, because when there is frequencies, right? And when we get to the frequency of the rocket or the launching mechanism, it starts to resonate with our satellite. When it gets to resonation, that has impact, really bad impact on mechanical components. So by this resonation, we can lose connections, misaligned parts, and weak joints can fail under the vibration stress, like they can be torn apart or anything. So the whole satellite can be torn apart, and that is something we really don't want. And the main purpose for everything is that we don't want to damage anything else in the rocket. Like, it's when CubeSat will die, it's like the smallest thing next to the damaged rocket, right? Another thing, outgassing, silent threat to CubeSat missions. Why it's silent threat? Contamination of optical surfaces, mechanical issues, thermal issues. What is outgassing? Outgassing is that when we are creating a steel or some material we are making a structure of, there can be like small bubbles or molecules of the air or any volatile gases in it. And those gases in the vacuum want to get out. So when they are getting out, they are going through the structure and they can damage it. As you can see here on this picture, it's for polymers. Polymers are really like the worst material in this. They have so much those gases in it, and it can lift the material, make bubbles, and damage all the, when we are talking about technical documentation, we have some tolerances. Those tolerances are, let's say, thrown away from a window by this outgassing. So how we can mitigate it? Right material selection, then the thing called baking. We have like thermo-vacuum chamber when we bake our structure before, like on the Earth, before the launch, and we can do that outgassing before it gets launched. So that's the mitigation and design considerations. We can count with a little bit of outgassing, of course, and just the things that will be damaged, or let's talk about these optical surfaces, we will move them away, far from the material that we know about, that there will be outgassing in vacuum. With the optical surfaces, it's pretty hard because when we have camera or anything, those gases can just flew away into space. They are like holding on our structure. So it can come to that we have some lenses, and those gases will make a thin layer on those lenses, and it can change their focal length, or if we have some lasers or anything, and let's say we shoot the laser, those can burn those gases or anything, and it can damage our instruments. So, space challenges. There are so many of them, and engineers are used to fight them. But there's just a small amount of them: microasteroids, orbital debris, extreme temperatures, radiation, communication delays, etc., etc. I think the comments are pretty for everything. Make big holes, can make big holes too, even bigger holes, everything. Extreme temperatures, material stress, radiation, degradation of materials, mainly for the polymers, and communication delays. Schrödinger's cat. I hope everyone is familiar with that one. So we don't know if it's alive or not. So another beer game. Please hands up. Who was on the last space beer? Okay, so maybe you can remember something from that. So this is only for one beer, and I want the dimensions of the ball and dimensions of the hole. Klarko? Anyone? Yes? Yeah, sorry, please wait for the microphone. My mistake.
Kdo se hlásil?
Pán v modrém triku. Is it working? Yeah, sorry, it's not working. I will give you mine.
The holes should have 10 centimeters in diameter and the ball 5 millimeters. Not?
So close enough, but any other guesses? Okay, guys are there? Yeah? No? Okay. So here are the dimensions. So 12 millimeters is the ball, and I don't have dimension for that, but I think you are close. It's about, I think, 15 millimeters. Sorry, 15 centimeters. And yeah, what is interesting about that is it working? Yeah, right, thank you. So impact at 6.8 kilometers per second, which is equal to 56 and 500 joules. It's a great amount of power, right? Due to it's only 12 millimeters in diameter by that ball. In these situations, I like to compare things to something we can better imagine. So, yeah, everyone I hope knows this guy. So, Mike Tyson. There can be another guess. How much you think that how big amount of joules have a Mike Tyson sponge? One guessing? Okay. Tyson's punching power was estimated at around 1,600 joules. So yeah, about a ball, about 12 millimeters, have 35 more power, 30 times more power than Mike Tyson's punch, which is, yeah, then pretty good for that small ball. So we are continuing with presentations. Space challenges still. Yeah, we can see them everywhere. It's space debris or like small balls or anything, or microsatellites. And we are not talking here about radiation or anything, because it's like a small amount for the structure that needs to hold. The space debris is like bigger deal for that. Here you can see a picture that is from the ISS. They have those problems like all the time. All the time is something hitting the station. You can see like those white dots on the glass, but it's good. They like made it out with the engineers, so yeah, they are safe. This another picture is too from ISS, and here you can see Sentinel-1. I wanted to give a picture the diameter of this hole because it's pretty big solar panels. And I'm sorry I forgot that one, but if anyone know that for Sentinel-1, how big was that incident? Okay, so a lot of us here are definitely on the university, so it's a self-learning time, right? Yeah, so here we have another fun fact. There is a list of countries that have like that are dangerous for the satellites, that they have like defense mechanisms, anti-satellites missiles and something like that. So in one country, they say to themselves, why we are not on that list, right? So they make the missile and shoot their own satellite. It was successful, it was big cheering up, but that incident made a really lot of space debris. So yeah, we can cheer up that we built a good missile, but we didn't look up for the consequences. And another way how to make it to space industry, right? So we are getting to the end, simulation and testing. We have thermal vacuum simulation, vibration testing, shock testing, EMC testing, radiation testing, etc., etc. Our guests today will talk about more detailed about thermal, and just a small amount of information from my side. Simulates temperature fluctuations and vacuum condition of space. And what's the main purpose of the CubeSats? We know to know if the thermal control system is working and if we can move in like optimal operating temperatures. If you have anything, so some device like earbuds or anything, you will always see in the manual, if you're looking into the manual, that there is always like information on operating temperatures that are optimal. And we are moving here like about -20 to +60 degrees of Celsius. Then some vibration testing. Reproduces the intense vibration experienced during the launch. Testing the structural integrity of a whole assembly and its components. As you can see on the picture, we place it like on the big table, and we can call it that we want to destroy our satellite, but we don't want to, but we need to. I don't know how to call it. It's set time for structure engineer, because when he destroys, it destroys. He did it bad. What to do else? Just work it on again. What can go wrong? This is like lessons learned on these presentations. Everything can go wrong. And one of another beer game. So single point of failures. What is it? Single point of failure is something that we can like have a part or some assembly, anything of that, and those are the single points. And if this point will fail, the whole mission will fail. Just it could be anything. It's not like a way back from those single point of failures if they will fail. So for the informations, mission Mars Perseverance had about 80 to 90 single point of failures. It was one of most hardest and dangerous mission in that topic. And now, again, questions to you who looked on a Netflix series. How many single points of failures had James Webb Space Telescope? No one? You can guess. 20? Okay, another guess? 40, 10? Okay, we are getting closer. It's about 344 single point of failures. So we can definitely call that an engineering nightmare. Because if we just imagine that, I think 2 years, that was like opening up the satellite and was traveling to its point, the launch itself, it just took off about 50 single point of failures. So when it was already in space, there was still about 290 single point of failures, which is crazy by me. So yeah, I hope you enjoyed this presentation. Thank you for your attention, and yeah, I'm open up to any questions. Okay, no questions. So I will call it the, okay? One question.
Hang on a moment.
Just a small question. What about these Japanese wooden satellites?
Yeah,
do you know any information about that?
I have information about that. It's hard to say. I don't know more details, but from my point of view, it's really hard from outguessing. The wood is, let's say, next to the steel. It has hollow parts in it with the gas or anything. So I don't know how they are managing with that one. So, but I'm holding thumbs. It's definitely let's go green with that. But it will be hard for me, yeah.
Okay, so I've heard about a scenario where throughout the vibration testing, they weren't careful and they didn't shield their components, with EMC shielding. So afterwards, when they took the satellite and put it into the orbit, it was magnetized and it was facing the wrong way to the Earth. Do you know about any other scenarios that could happen, something similar or something so destructive or mission disruptive like this?
That's a tricky question. I don't want to be the pessimist, so no. I don't know about any other situation that will happen. I hope I answered your question. Yeah, in the space industry, you don't want to be the pessimist. You want to be the optimist. Everything goes smooth, everything goes right, until it wouldn't. So yeah, any other question? Okay, so thank you very much for your attention again. And now the 10 minutes break. You can get beer again, and then will be presentation of our guests. Yeah. Okay, so the pause is nearing the end. So everyone buy the last beer, please, and sit down. Or you don't have to, of course. I would like to introduce our guest, Roman Dohnal. He works in LKA Engineering and is working on thermal analysis. Okay, so now I'm leaving it into your hands.
Thank you. Okay, hello everyone. So let's start the presentation and some talk about spacecraft thermal control and the environment, hazards, and other influences that are important for the design of any spacecraft that we want to have functional in space. Yeah, so maybe a short introduction from my side. I'm a thermal engineer. I do the job quite a long time, something like 12 years. And the part of my job is to do the analysis and maybe proposal of changes or design alterations to fit the requirements and all the specification that needs to be fulfilled. The ECSS standard, as it was presented in the previous presentation, that's let's say a small Bible for us in space industry. So it's good to know where to find it and how to read it. It's not that complicated, so it helps a lot. And the paper is able to help with questions and maybe specify what needs to be addressed and evaluated during the engineering part of the spacecraft. And I will, let's say, just scratch the surface of this problematic because it's really deep and maybe vast information is ready. But I would like to aim for something like 30 minutes with the presentation, and I will, let's say small details, but not go into the deep detail. Yes, like that. Okay. So, what is a spacecraft? Yeah, it's quite broad term. Yeah, because usually we imagine something that orbits some space body, a planet or a moon, or tries to travel into this deep space. But also we have to consider that it can be something that is touching a surface of another body. So like Mars rovers or moon landers, Venus landers, and this is a CubeSat. You already know that, and some space probes and some telescopes. Yeah, usually like that, and many other forms. Yeah, so. Basically, everything that is behind some altitude level of our atmosphere is considered in the outer space, and therefore it's a spacecraft. So, size matters. That means the design, the obstacles, the problems, and the solutions really rely and depend on the size of the spacecraft. So you have already heard about what is important for CubeSats and small sats, or even smaller satellites. My expertise is more from the field of middle-sized and large spacecrafts. I've been working on a project, ESA projects. I will start with the smaller ones, with a small component on a satellite that was dedicated to synchronization of atomic clock on the spacecraft with a laser. Yeah, so that was my first analysis in this field, and then I progressed to other small projects. But the first one and really large was the Euclid mission, which was launched last summer and is now in operational state. And send really nice pictures. Yeah, take a look. Yeah, if you are interested, there is a website which is able to show you in 3D sphere the photos and, let's say, pictures from several ESA spacecraft like James Webb, Euclid. I think there was Gaia, and some other I forgot already. Yeah, but you can go through the ESA website and find this kind of library of photos. And what is really interesting, you can see the change of resolution and the information contained in each picture and compare it between the James Webb telescope, Euclid telescope, other telescopes, and so on. Because, let's say, we tend to photograph the same locations many times in various wavelengths, yeah, in UV, infrared, X-ray, and so on. So we have different views of the same spots on our sky. And that's quite interesting. I was quite amazed. So sorry, I don't have the link on me here, but you can click through on the website of ESA. So I've been working on the Euclid mission. Currently, I'm working on the Ariel mission, which is also middle to large telescope. I have a small footstep in a JUICE mission. There was a RIME antenna, and I did some thermoelastic analysis on that. So let's say in the years I spent on this topic, I had some nice experience. So hopefully it will be interesting for you. I guess I will progress like that. Yeah, so the space environment, yeah, it's really not nice place to live. Yeah, so each spacecraft or satellite needs to survive, really survive quite harsh environment. So yeah, I started with extreme temperatures, but maybe that's not the most harsh. But anyway, we will take a closer look on that in later slides. Then extreme heat fluxes. Yeah, for example, the sun is a nice source of heat, but if you are too close, it's not that funny for the satellite. So the design has to accommodate what is necessary to overcome. Yeah, the planets can be cumbersome also. Yeah, I will talk about that later. Yeah, I tried to push extreme before the radiation, but not much space there. So yeah, there is an emoji for that. Yeah, the radiation is quite harsh also, because shielding is possible, but it's not absolute. Yeah, I guess the CubeSat people know that, and they have to overcome that factor also. So solar particles are really funny for the electronics, and cosmic rays is something deadly for the electronics, because if a cosmic ray hits, for example, the memory bank on the PCB, it can flip the 0 to 1 or the other side, and yeah, a whole program can be stuck, and that's usually a problem. A big problem, yeah. Space debris, I guess that was mentioned here already, and extreme maneuvers, that means the funny parts of mission like aerobraking or landing on a body, for example, the Mars. So yeah, these are the external ones. And the time, yeah, that's our problem, because each of the mission, because of our current technology, we still have to overcome really long distances in space just to arrive to another planet. But our means of transport are really slow. Yeah, so it's quite common that when a team starts a mission, it takes 20 or 30 years to finish the mission and say, okay, we did it, yeah, we managed. If you take a look at the YouTube and try to look for the Cassini mission that was orbiting Saturn, you can see the team, how they got old, from young postgraduates starting with the project, and let's say senior, almost getting retired people. That was their lifetime spent on the project, and they did it. The Cassini probe was really successful, and they extended for another. I think they started with 6 years normal operation, and then extended another 8 years operation. And that much robust was the design of the spacecraft, and that is wonderful. Okay, so is it impossible to survive there? It's not that heavy, because humanity has quite long, several decades history in overcoming these extreme conditions. So let's say first attempts were about getting the knowledge of what is outside our atmosphere. So the first missions were just suborbital launches, just to measure what is the pressure, what is the outside relative temperature, but with low density temperature, low density atmosphere, we cannot talk about the temperature anymore because it works slightly differently. But anyway, just to know the environment. So I proceed with the extreme temperature. So it is said that the space is really cold, but in reality it's not cold. It just lacks any other body that would reflect or emit the heat towards our satellite, or if we are the astronaut or cosmonaut, towards our body. So just to simplify, anybody that is floating in the space, it radiates its own heat towards space and nothing comes back. That means it will lose temperature, and if it does not have any thermal control system or internal heat source, it will cool down to almost absolute zero, but we have something like residual background radiation, and it is around 3 kelvins above, 3 kelvins, that's 3 degrees above the absolute zero. So it's really relatively cold, but not absolute zero. And here on Earth, we are quite lucky because our planet is orbiting on something that's called habitable zone. So it's, let's say, distance from our source of heat, that's the sun. And we are at the, let's say, just fine distance from the sun to have reasonably normal, or let's say, favorable temperatures here, to have liquid water, to have atmosphere, and the third factor, but it's not, let's say, environmental, it's that we have the internal magnetic field that is generated by the Earth's dynamo effect inside the core. Without the magnetic field, we would not be here as a species. Probably no life on Earth would be possible. So let's be happy that we have this nice home. So what I wanted to stress out is that if you are orbiting Earth on low orbit, the satellite can encounter plus minus 150 Celsius. The minus temperature is when you are in the eclipse behind the Earth, and you don't receive any solar flux. But if you are outside the eclipse, so you are orbiting in a special sun synchronous orbit or something similar, and avoid the eclipse, you have something like 20 degrees equilibrium. It's let's say it's a term, and it is calculated somehow, and it depends on the spacecraft spacecraft surface properties and design in general. Yeah, but what is nice? It tends to be near 20 degrees. That's the reason why the CubeSat, for example, don't need heavy thermal control system. Yeah, if the components inside are robust enough, they don't need any additional heating, and they will be still around plus 20 degrees. But it depends. Yeah, it's not automatic. It needs to be a smart design on the side of the CubeSat or SmallSat. On the moon surface, you can encounter plus 120 on the sun illuminated side and minus 170 Celsius on the dark side, on the non-illuminated part. Yeah, the fun about moon is that it turns around Earth, and it takes approximately 14 days to be. One spot on the moon is illuminated for 14 days, and another 14 days is in the dark. Yeah, so anything that lands on the moon needs to survive this. I hope you watch what is happening in the whole world space industry, and you would probably know that on the moon already there were the USA landers, the Apollo mission. Yeah, so that was decades before, but now quite recently China has landed there, India has landed here somehow. I think Japanese JAXA space industry is planning some mission to land there. We, as a Europe, almost had a lunar lander, but when we finished it when we finished it and optimized it, they scratched the project. So, yeah, and that was 10 years ago. And I hope that someone in ISA is now bumping his head that we should not cancel that project, because Europe could be one of the, let's say, older countries or lands, I don't know how to call it, that could land on the moon and do a science there. It was not just to land there and show, okay, we are here, what to do next, but it was planned to carry some instruments and do the science on the moon. So, yeah, we missed it. So now we are at least 10 years behind the rest of the world. So if I continue, yeah, the Mercury is quite living hell because on the sun side there is plus 400 something degrees, and on the dark side it's minus 180. Yeah. Mercury, similarly as Moon, it is tidally locked. That means it does not rotate with respect to the surface of the sun. That means, if I say it differently, we see still the same face of the moon, right? Did you notice? Yeah, hopefully yes. And the Mercury does the same thing. Yeah, it never faces the other side to the sun. So there is a quite funny planetary and orbital mechanics causing something like that. If you have a quite long time, it's quite probable that the body will stop the rotation and starts to be tidally locked. Okay. I said that Mercury is a quite small hell, but Venus is even more hell. Yeah. So if you are trying to survive the air braking through the atmosphere, which is not that difficult, you will land on the surface, and the surface is plus 460 degrees, which is temperature quite above of liquidation, not that word, but you know, of some metals. So if you have a simple PCB, it will melt away. Yeah, so not useful, but Russian Roscosmos managed to crash several Venera spacecrafts, but I think 3 times they managed to get also some science. And I think that from the surface of Venus, there is only one set of pictures that were taken. No other country managed to go to Venus. Yeah, so we have a few small bad quality photographs of Venus surface. Yes, and as a contrast, Uranus, which is let's say our furthest planet, it is a gas giant once again. So we think it does not have a surface, but near on low orbit of Uranus, it's something like minus 220 degrees. Yeah, so that's quite harsh. The problem is that far from sun, we don't have any source of power. Yes, the source of power is our sun, as I already said. So I tried to create a nice table of solar constant, which is the heat flux received from sun on some surface. Yeah, so if you send a probe, something like Bepi-Colombo mission, it goes to Mercury, and it has an orbit around the sun and Mercury together. We don't have enough delta V to park on the orbit of Mercury. Not yet. Yeah, we cannot do that right now. But we can have some semi-elliptical orbit around these two bodies. And at the orbit of Mercury, you receive 9 kilowatts of heat per each square meter. So if I consider that I'm something like 1 meter squared, I will receive 9 kilowatts and get burned definitely. Yeah, and immediately, definitely. Yeah, so on Venus, it's slightly better. So a good sunscreen should work, 5,000. Near Earth, we receive 1,400 watts per square meter and Kelvin. That's what we take as a resource from sun, and let's say our atmosphere, our biosphere, everything benefits from that heat flux. Just a small detail, this value is at the low orbit, so above the atmosphere. Here on the surface, near the sea level, you have something like 1,000. Yeah? So we lose 400 watts per that crazy unit just by going through the atmosphere. Yeah, so we have something like 1,000, therefore it's easy to calculate everything on the surface of Earth. Mars is further from the sun, so there is something like 340. On Jupiter it's only 50, and near the Saturn is 14. And beyond Saturn, it's almost zero. Yeah, you don't receive any reasonable heat flux from sun. You just see a small dot on the sky, and the sun seems to be just a brighter star when you take a photo in that direction. Yeah. So if you take a look at the mission of Voyagers, or the mission that I already forgot, the one that tried to photograph Pluto. I forgot, sorry. So it did turn around and try to take a picture of Earth and Sun, and there was basically nothing to see. Yeah, that was too far, and you don't receive any heat there from that. So other heat sources for the spacecraft are the solar flux. Already talked about it before. So planetary infrared radiation. Yeah, the Earth itself is not absolute zero cold, so it emits the heat, which is let's say if simplified, it's some sort of gray body radiation. Yeah. So you receive something like 150 watts from Earth. If you are on the sun side, you can get something like albedo, and that's the reflection from the surface back to space. And if you have a spacecraft orbiting the Earth, you receive also the portion of the solar flux that is coming. For example, C is not that much reflective, so you get something like 30% back. But above the ice, you get 80% back. Yeah, so if I get back slightly, and on the orbit, I receive 1.4 kilowatts, and multiply it by 0.8, I get almost 2 times the the solar flux on the spacecraft. That means I may become overheated if I don't have any means how to control the temperature. Then there are some crazy maneuvers like atmosphere drag and heating, aero heating, and let's say entry to the atmosphere. So, for example, if you have a spacecraft that tries to land on the Mars, you have 50% chance that the injection to the atmosphere and the landing will be successful. Yeah, people tried to land on Mars many times, and it's 50 to 50 chance that it works. Now with the NASA, with the space cranes, and with the technology that seems to be really robust for that, they managed to deliver the rovers, the Perseverance, and the previous ones. And yeah, they are using the space crane, something that tries to land here, hovers, and then on the rope they will put a rover on the surface, and then it flies away and crashes somewhere. Yeah, but this concept is really nice. The problem with the Martian atmosphere is it's too thin to have a good aerobraking, but not, let's say, it's still too thick to be omitted or neglected. Yeah? So if you are flying really fast through this 1% pressure of Earth, you still have a lot of drag. Yeah? So if you are building a spacecraft, you need to account for that. And also, yeah, the other problem, the opposite problem, is absence of the major sources. So if this is not present, you don't have any external heat source. Yeah, for example, in the eclipse, when the spacecraft goes behind the body, it's usually a not good situation for the spacecraft, and it needs to be prepared accordingly. So, just quickly, radiation and space debris. You have already seen this picture. Yeah, that was nice. I like that too. This is really similar. Yeah, I guess this was something like a grain of sand, but with the velocity that had relative to the panel, it can create quite nice holes, and this is something similar. Here on this picture, let's say this is a simplified map of the particles and pieces that are around Earth. Yeah, so low orbit Earth, and larger orbit Earth. And there should be visible the geostationary orbit, which is in some distance, and it's useful for having a spacecraft looking still at the same spot on the Earth. The problem is that there is a lot of debris, and some organizations try to map the debris, but the problem is they are using technology that allows to reveal something that is a few centimeters and bigger, large. Yeah, so everything below centimeters is still really dangerous, but we cannot detect it. Yeah, what we can do is try to monitor the launch, and if there is anything that is discarded from the spacecraft, they need to remember the trajectory, the speed, and the possible orbit that it will take. And then there are some people that try to calculate how many years it will take when the orbit gets distorted enough to get back to the atmosphere and burn. What is not lucky for us, some orbits are really stable, and the debris will be there quite a long time. Yeah, let's say several hundreds years. 1,000 years. Yeah, really long time. Yeah. Okay. So, what a spacecraft needs to have or needs to fulfill in order to be successful, right? So, in previous presentation, we somehow bite the structural integrity, the loads and thermoelasticity. This is really something important because if the spacecraft gets apart during the flight, during the launch, during the flight, some maneuver, or during the final phase when the science should be done. It's not useful and it's a failure. Yeah. So another picture of vibration table, and yeah, that's it. Yeah, thermoelasticity is a problem. Everything that we use has some expansion with temperature, and with the bad combinations between the materials, you can create quite high stresses. And when we want the structure really lightweight, we make them thinner. And that means that the high stresses at thin cross sections means fracture, and yeah, it's a blast. Okay. So this is a long, but I will let's say go really fast. So what we use for building a spacecraft, this is more focused on the larger spacecraft. Yeah, in the CubeSat you have this Lego assembly, and you put everything very similarly. But the larger spacecrafts are tailor-made. Yeah, they need to have the structure just exactly what is necessary for the mission and for holding the instruments in the right place and pointing the right direction. Yeah. So what we usually use is aluminum or carbon fiber face sheets. They can be reinforced by honeycomb. Therefore, you have a sandwich panel. That's let's say the building block of everything. You have a lot of milled parts. Yeah, either from aluminum, titanium, or steel, Invar, and other special things. There is a silicon carbide, special ceramic material that is really stable, but really fragile or brittle. Yeah, but really good for optical components. Some joints, so you can use bolts, zip ties, and Kapton tape. Everything in space is took to the place with a Kapton tape. Yeah, that's the standard. Yeah, then you have to create some sort of insulation from the outside and also inside sources of heat. And therefore you use MLI, which is the multi-layer insulation, some quite good idea how to insulate something. Thermal breaks and standoffs. When there is a computer, some unit or some instrument inside the spacecraft, and it generates the heat, let's say it transforms the electric power through resistance to heat, you have to get rid of it, because otherwise you will burn or overheat the unit inside. Therefore, you need to accommodate some heat path, usually it's a conductive path, from the unit, its interface towards somewhere else, yeah, where it does not have the impact or negative impact. Usually we bring the heat from the unit or from the computer to some structural panel below. The structural panel below should be able to spread the heat away and maybe radiate it towards space via some external radiator. Or a panel, a structural panel, which is not covered by MLI. Yeah, that's also a design. Some doublers, that's let's say something that helps to spread the heat, and heat pipes. Yeah, I guess you all already seen a heat pipe, because if you open a PC like that, and you take a look at the graphic card or the CPU cooler, there are usually heat pipes because it's really effective, but the heat pipes have a limited range of operation. So if you are above or too low, it does not work. But there is a, let's say, 10 or 15 degrees sweet spot when it can transfer really a lot of heat in long distances, and that's important. Okay, then you have to control the temperature levels on some locations. So you need active thermal control hardware, like electric heaters, let's say simple snake with a resistive path, and it generates heat, and you measure what is the level. Yeah. Then there is AOCS, that's attitude orientation control system, yeah, something that knows where the spacecraft is looking. That's especially important when you have some optical instrument, yeah, some telescope, or something that measures, and the orientation is important. Okay, And also, let's say, the service units like communication, power source, and sometimes there is a payload. Yes, so usually computers and instruments, or instruments and the computers that try to process the image and then send it to communication units and then transfer it to Earth. Yeah, we want the data that we collect in space, so we have to do. And I have not listed a lot of items because otherwise I would need 3 slides like that. Yes. So this is Euclid. This is my baby. So here we can see the design and let's say this uncovered surface. This is a big radiator. Yeah, it uses this tube to reject the heat from the main base plate. Yeah, it's also not covered. Unfortunately, it's not that easy to see because this is the silicon carbide optical bench, the big plate from Ceramides, and it's really dark. Yeah, so not easy to present. Sorry for that. And the other parts are covered by the MLIs. A common mistake is that it's golden. It's not golden. It's just the funny color that has the foil, the polyimide foil, and yeah, it's more like amber or something. Yeah, that it's not golden, but golden MLIs exist. Yeah, just to say. Or it can be VDA, so that's aluminum deposited on the film, and other. Yeah, also black MLI is possible, white MLI is possible. Yeah, for example, the spacesuit for all spacesuits, they have a special fabric, and it's also some sort of MLI. So the astronaut have a suit, yeah, tailored for usually his dedicated body, yeah, exactly for him, for good tailor-made dimensions. And they are, let's say, inside a MLI suit, and the surface layer is really special because that's the Betaclot, NASA design, and it's really useful to survive the environment around Earth. Yeah, we still don't have to create spacesuits for other planets because if Elon Musk succeeds, the Mars missions are close. But if not, yeah, we still have some time to figure out what is needed on Mars, for example, or the Moon. Yeah, for the Moon, the Betaclot spacesuits are still good. Okay, so let's say this is a structural dummy. But this is the inside of the spacecraft, 2 instruments, and so on. I will not go into details because I would talk another hour about that. Yeah, I spent 8 years on this project, so I probably know every bolt everywhere. Yeah. So just a quick view. This is the aluminum sandwich panel, the most basic building block of any structure for larger structures or larger satellites. This is the CFRP, so carbon fiber reinforced sandwich panel. The faces are CFRP, and also the honeycomb inside is CFRP. That's quite a special thing. Yeah, because usually, even if you have CFRP face sheets, you have aluminum core. Yeah, so this is, let's say, another level. Maybe I will answer the question about the wooden CubeSats that, the news that came today in the morning, or at least I read it this morning. Wood is also a good material, probably, because it's quite strong and maybe lightweight enough to be used. But as my colleague said, I would be worried about the moisture that could be trapped inside the wood, because wood is really porous, yeah, and when it grows, it's full of water. Okay, if you bake the wood and try to evacuate the wood, yeah, there are still a lot of moisture inside because that's a problem. So I guess it's possible, but I'm not sure it's practical, yeah, because of the outgassing problem. That's the major, I guess. The other thing, wood is not thermally conductive, which is good and bad in the same spot or at the same time. Yeah, sometimes we need to conduct somewhere the heat, and sometimes we don't. And well, it could be useful for when we don't. But anyway, I would not use it for larger structures when there is, for example, some optics, because optics, yeah, sorry, I'm still stepping away from the camera, sorry. And okay, and yeah, that's the reason why it's not useful. For example, the Euclid mission, after half of the year at the orbit, it got 2 layers of molecules, of water molecules on the surface of the VIS instrument. Two layers of molecules. So let's say really, really thin, many times thinner than human hair. And it already degraded the sharpness of the picture by 15%. So they spent 14 days just to be sure how to decontaminate the internal cavity with the mirrors and the instruments and so on. It's not a surprise. It was by design. They knew that something like that will come. So they had a tip that this one of the many folding mirrors, there was they said it seemed to be the coldest one, and maybe it was the one having the layer. So they heated the spot by 20 degrees up from the normal level, and they got rid of the vapor. Yeah, they cleaned the picture, and then they put it back to the same level as it was. Yeah, the contamination is a big problem, especially if you have optics. And the main source of the water are the MLIs and everything plastic. Yeah, so if you put something that is nice and helping and insulating, you also create a problem with the outgassing. Yeah, but everything outgasses. Also metal. Yeah, but not that much as the MLIs, polyimide, and all plastic components that are present there. Okay, so. Yeah, so wooden CubeSat is definitely possible, but okay, for larger satellites, I cannot imagine that it would be helpful. And it was one of the goals for wooden CubeSat was to save the environment. I don't see a big gain on that because the most polluting is the launcher that gets it to the orbit, and yeah, it's small, it's lightweight, and the piece of aluminum and some steel is not that energy heavy, like burning several hundreds of tons of the fuel. Yeah, so okay, I think they wanted to try it, so it worked. But let's see when we see some data from that. Okay. And yeah, another fundamental building element is a milled part. Yeah, and this part is created from a single block. So you purchase something like 300 to 500 millimeter big block and keep just this. But meanwhile, you create a lot of shavings, which is nice, but useless. Yeah, but okay, we don't have any better mean. Okay. And thank you for listening that long. Yeah, I stretched it for 10 minutes more, but let's say hopefully it was interesting enough and you can enjoy. Also, I have another slide. Yeah, let's say this is the contact for the LK Engineering Company. If you know someone who is interested in the topic, yeah, contact us. Yeah, we have some nice work to do. Okay, all these I somehow participated. Yeah, this is the additive manufacturing. I did somewhat optimization on that. This is the Athena diverter. I did some optimizations on that. Euclid. This is the Ariane 5, I think. Some Flutter. Over there is a lunar lander. We almost finished it, but okay, it got cancelled. And this is the fairing for the launcher. I did analysis on that, yeah, and many, many others. So I guess that's all. And maybe it's a good time for questions. if you have any. Yeah, the gentleman with a nice beard there.
Let's go back to the wooden constructions.
Okay.
Because from the report that I've read today, they also mentioned that they want to use it for buildings on Mars or on the Moon. What are your thoughts about that?
It's a mass that needs to be transferred from Earth to Moon. That means expensive and not useful. Yeah, let's say my most favorite method how to build something on Moon would be use the local resources. That means use the regolith that is there. If you take a look at the composition, it contains a lot of aluminum, a lot of silicon, a lot of iron, sorry, and it can be used for steel. It contains also some moisture, so water is present on the poles. We know that there are a lot of water on the poles in the craters, hidden. Yeah, quite surprise for us. And therefore, I would do everything inside. Yeah. For example, if you take a look what can be done, yeah, for the buildings, I'm looking forward to the time when we mix some glue or something that will stick together, the regolith together, and we will build domes or buildings from that part. And we will just transfer the technology and then build everything from the resources that are already there. Yeah. For the wood, it's still heavy too much. Yeah. If you want to have a structure, take a sandwich panel. That's the most optimal what we have. Yeah. It's the strongest and lightest material that can be used and is strong enough and is, let's say, cheap enough. Yeah. Because the price is really, really important. Yeah, that's, let's say, something that Elon Musk with SpaceX is now focused. Yeah, because we already did expensive missions. Now we need something cheap and frequent to do what we intend on another bodies. Yeah, on the Moon, and probably the first one would be the Mars. Yeah, but yeah, people had quite a long time to dream what can be done on other projects. Another planets. Yeah. And there are projects that are focusing on science and also on resource mining and resource gaining. And for example, I'm quite looking forward to the JUICE mission, which is now heading towards Jupiter, Ganymede, the Enceladus, and the other nice moons. And one of them is I think Enceladus is now the best candidate for having a life there because there is a subsurface ocean probably. Yeah, there are some water, how is it called? Water deposition towards high altitudes above the surface. Yeah, so they want to fly through that and see what's inside. And if we find out that, okay, this is water, it's not that salty, or it's salty really heavy, and we can extract what is inside, dry it, and have the resource like that, yeah, we can build on the remote places easily, and let's say cheaply, and in a good time prospect. Yeah, it's not 100 or 200 years in the future, it may be just 50. And that means that you will see it, and I will maybe see it when I'm dying. Yeah? So that would be always quite nice. Yeah, hopefully that was the answer.
Okay, I want to ask, with your experience, if you ever encountered any problem that I loved your slides where you are using word extreme and there was an impossible meme. If you ever encountered something like that you said to yourself that it is impossible, but still you were working on it and somehow managed it.
Yes. No, okay.
some details?
That was a dramatic pause. No. Actually, yeah, we have a reflex to say this is impossible. Yeah, we see that and okay, it does not count together. Yeah, what to do? But let's say the method is try to make small steps and investigate what can be done. And if you make a step in some direction and it seems to be useful, yeah, okay, let's do it. And then take a look once again, because we are simple linear creatures and we cannot, let's say, do 1,000 possible solutions and then pick the one which is nice. Yeah, we have to do something physical. So yes, sometimes the design seems really not useful, not helping with the goal. But okay, there's always some compromise. Yeah, the compromise is the way. You cannot have both on unphysical at the same time. Either, yeah, there is, let's say, I don't know how to explain nicely. You have a resource that can be split, and you just try to find the balance, which resource should be there and which resource should be there. For the design, usually, yeah, the problem at the beginning, you don't have enough space to put everything inside. Yeah, for the CubeSat, it's I guess quite normal, but it happens also with the large telescopes. Yeah, you have, I don't know, three trucks of internal volume inside, but still everything is too bulky, yeah, too much volume eating, and then you have to play Tetris with everything. Yeah, so usually means we have to find a compromise that will fulfill everything we have, and yeah, use the resources that we have. But there is a moment when you try to find really a lot of ways which could help, but the solution is not found. Let's say the inputs and the outputs are not able to meet. Yeah? You don't have the cross-section of two lines. That means that the concept needs to be reorganized. Yeah? That's that path that you took, and unfortunately it's not nice. And then there's the reflex to say it's impossible, but that means just that you selected the wrong assumptions at the beginning if you find that there is no solution. And sometimes, or maybe always, my colleague is smiling, but okay. Usually it's ECSS that's not helping, yeah, because it contains a lot of factors on loads, a lot of factors on limits, a lot of factors in between. And when you calculate and find, okay, it's this value, you find out that you are 10 times over. Yeah, so, okay, where's the solution? Yeah, there's no solution like that. Yeah, you have to consider the mission once again, the solution once again. If it's a stress, you have to find the way how to ease it. If it's an extreme temperature, you have to either isolate, or if it's too cold, you have to heat up sometimes. Sometimes it's cheap, so you just connect some hotspot with cold spot, and they will find some equilibrium. But sometimes you have too much dissipation, and you need a larger radiator on the side. And that's not easy because the system level says, you have just this surface, yeah, deal with it. Yeah. So then you have to go to another technologies. Yeah? We have something like cheap, easy ways, but there are also the problematic ways, or something that is not that easy to implement. But since we have the technology, it means someone before has already tried to solve similar thing. Yeah, so yeah, we have something like 70 years of solutions. Yeah, so if you are at the end of the solution, take a look at the old NASA papers, because they were really creative how to do something. Yeah, so, okay, that was quite long. Okay.
Thank you.
Someone else? Yeah, maybe just a side note, yeah, redundancy is really important. Yeah, the single point failure, yeah, it's something that can really bury the satellite at the mission, and that's not well received from anyone. So if you can minimize these points, it's really useful. But it's not possible to get to zero. Yeah. I would like to react that you said you have to be optimistic and not pessimistic. Unfortunately, that's not the engineering way. Yeah, you have to be pessimistic and be sure that you can be optimistic. Sorry. Yeah, so yeah, let's say you have to be pessimistic enough to investigate, to know that the design is robust enough in order to be, okay, that should be fine. Yeah, you cannot accommodate every possible failure opportunity. Yeah, it's impossible. Therefore, from CubeSat, you would angle the satellite to something like a tank. Yeah, it would be really heavy and not useful. So you cannot do everything really fail-proof. You have to make a compromise. Yeah, that's let's say something I've learned in the years in the industry. Yeah. Okay. We take also stupid questions if you like. No? Okay, so clever? Okay, I guess we can stop now. Yeah? Have a beer, I guess.
Okay, so really thank you very much for a presentation. We are glad you are here today. And now we will make a 5-minute pause. And there will be another presentation on ESA opportunities in some programs for, yeah, sorry, little luck in head. So 5-minute pause. Thank you. Okay, everyone, so 5 minutes comes to the end, and there will be another presentation for ESA launching careers by our other guest, Josef Pouzar. So thank you for your presentation, and I'm leaving it to your hand.
Thank you for your introduction. To start over, just a quick introduction of myself. I'm a PhD student of Brno University of Technology, Faculty of Mechanical Engineering. And today I'll be speaking to you about some possibilities of you, possibly as students, to participate at ESA. So may I ask you, are there any of you bachelor students? Bachelor, yeah? 1, 2, 3, most of you, okay. And masters, are there any? Something like that? And the PhD students, are there? 2. There are 4 of us. 5 of us, okay. So you are not alone. Okay, so my presentation will be partially about the possibilities of you as students. How can you participate in ESA, some projects, etc. And the second part is about my experience at ESA Academy, specializing in transfer of technology. So how you can possibly start a business, how can you transfer some patent from space technology into some terrestrial applications, etc. So one moment. So to start over, there are basically 3 categories that you can attend. The first one is the early career opportunities at European Space Agency, and basically it is divided into 5 parts, and it is based on how educated you are at the moment. So the first one, the student internship program, is for final year bachelor or masters. And it is basically an internship for a graduation, so you have to be at the end of your student something. It can help you in your final thesis. If you are doing something, you can participate on real projects and get a final thesis done based on this activity. And it's basically 3 to 6 months long. Can be also split it to multiple segments, and it's basically 100 students per a year. And the most of the students are staying in ESTEC in Netherlands, which is like a very big laboratory where there are a lot of people working there on the real space technology. The second part is Young Graduate Trainee Program. After you are graduated, you can ask or participate in this program, and it's only for masters, I must say. You have to have limited professional experience. This is the first requirement, and it basically prepares you for a job in the European sector in space segment. It's 1-year contract. It can be prolonged to 2nd year, and you get also a salary during this period. It's not so much for Netherlands or any country, but it's at least something. Then there is a national trainee program, which is not for Czech Republic, so basically it's only for these countries, and it's 25 national trainees per year, also some internship, and also it is paid. And the last parts are only for PhD students or postdocs. So if you are a PhD student or a PhD student at the end of your study, or you are a postdoc, you can ask for, or you can try to get a research fellowship, which is basically a 2-year contract at the location of the research facility. And it is paid job. You basically made some research, advanced research related to space technology, and it is something like 50 researchers per year chosen for this. And then there is the last one, which is for PhD students or postdocs, and it's co-founded of your research or something like that. This is what I obtained for my PhD thesis or my PhD studies. I'm currently in the 4th year of my PhD, so hopefully the last one. 2 years ago, I obtained this co-founding from European Space Agency to finish my research, to get a dissertation done, and it's basically funding, some mentorship, and etc. So if you are interested in this, then we can chat after this presentation about it. And then there is a ESA education program, which is basically for youngsters. I think that there is no youngsters in here. So it's basically activity how to get space to elementary or middle schools. In Czech Republic, we have ISRO, which is a platform where you can obtain some courses, some guidance, etc. for only teachers as well as the students. And then there's the last one, the ESA Academy program, which is the main topic of this presentation. And it is divided into 3 segments: the ESA Academy training, which we will be speaking about. This is for bachelor's, master's, and PhD students, and it doesn't matter from which segment you are. You can study medicine, and still you can apply for this workshops, courses, etc. It's basically 1 week, or maybe more, some internship or not internship. It's a workshop or courses, and it's focused on variable of segments of related to space. Then there is ESA Academy projects, Fly Your Satellite, which Y-Space managed to get into. Fly Your Rocket, Rexus, Bexus, etc. And also ESA encourages you to participate on some conferences. They can pay you some sponsorship for it, and to present your thesis outcomes and so on. So there is a lot of possibilities how you can participate with ESA. If you're interested in those, you can look it up on a website, ESA Academy or ESA Academy programs, and you can get some more information about it. We'll be speaking about the ESA Academy's training program, which is basically located in Belgium, next to Brussels, in ESSEC Galaxia. It is education center. You can get there for 1 week or more, depend on the training session, and the training session is for 30 to 40, 30 students, and it's for, I don't know, 8 hours per day or something like that. And the main reason for it is that you are focused on some topic, for example, thermal design of satellites, or transfer of technology they will be speaking about, and you work in groups, you learn something, you apply it to some exercises, and this is how you work. And for this, you also can obtain ECTS credits to apply for your study program. How to get to these courses or workshops? On this website, ESA Education or ESA Academy, there is a list of current opportunities for you as the students to apply for. There's also some deadlines, which is pretty much close to, or it is closed also, and this is still opened. It is renewed by, I don't know, daily basis maybe, I think. So please check it out. And if you are interested in anything, then you just open it, get some description of it, and fill a form, like an application form. Application form is just some basic information of yourself. You upload a motivation letter of 1 page, CV, and also you need a formal recommendation letter of your professor or some supervisor at Academy. And also transcript of grades. When we get to the ESA training, we were 30 of us, 30 students from bachelor to PhD, and we were told that there was like 200 applications, so it's pretty big chance to get there. So I encourage you to do it. How does it look like? This is like the education center, 30 chairs, 30 screens. In front of you, there is 1 to 6 experts per day that are talking about their experience, etc. And today we'll be speaking about my experience from technology transfer application and innovation workshop, which was in February this year, I think. And it was basically focused on space business development, how to settle up a business, how to transfer some technology into new things. So this is some photos from it. This is how it looks like. 30 students that are very confused what was happening. This is us. This is me, and this is my colleague Filip Čapka from YSpace. Maybe you can recognize him. It is pretty recognizable. So this is our schedule of our training. I put it in here because you can see that we started at like 8 o'clock and ended like 6 o'clock in the evening. So the day, special it was February, so the day started in like there was a dark outside, and when we get to the hotel, it was also dark. So our whole week was just a training center and nothing more. So it was pretty intense. We were really exhausted, but after each day there was a group meeting. We were drinking alcohol and playing some board games. So it was pretty fun. And now to the problem of some space business, transfer of technologies, etc. So what is a space company? Generally speaking, I do not have anything common with business education. So I'm mechanical engineering, aerospace engineer. So this is made of my notes and some presentations that I was provided. So if you have any more questions related to business, how to make a business canvas or something like that, I can answer only where my limits are. So please, I hope some information will last in your brains today. So what is a space company? A space company doesn't have to be always like a SpaceX with a lot of rockets, a lot of rocket engines, and so on. It could be also some company that works in a clean room that are assembling satellites together or making some parts of it. But the space company could also be this guy with his laptop and his harvesting machine, because this is new age of if you are a farmer, you have some field, you are planting crops, then there you are interested about the soil moisture, for example, or some animals that are ruining your crops. So you can use satellite data to provide you with more information about your soil or your lands and about your plants. So this is also a space company that are using satellite data like GPS data or some weather forecasts from space. So basically, this is GPS visualization or satellites of these constellations that are making your position or defining your position on the Earth, and you can transfer it also for another companies. Like if you have GPS, you can transfer the GPS signal or GPS data into something in sport, for example, like this company, Johan, that are doing this eggs, or I don't know how it looks, and basically they put it in this costume, and they give it to some sportsman, and they are measuring their heartbeat. They are measuring their location on the field, and based on this, they are making some decisions of how to improve their play or something like that. So this is, for example, one of the ESA's business incubated business. So this is how you can transfer the technology from GPS signal to a real company that are located in sport environment. So what about this transfer of technology or technology transfer? What it is? If we have a rocket, which is pretty big thing, the critical parts are the engines, for example. So if you look at the nozzle of the engine, it has to withstand really big temperatures, really high temperatures. And how to deal with it? You can either cool it somehow with, for example, some tubes that are running around the nozzle, cooling it down, or you can use some advanced materials like carbon ceramic materials that are used for these nozzles. And this material could also be used in another applications, like, for example, a braking system. Because if you are using brakes like this Ferrari brake, you have to dissipate the heat energy that generates when you brakes. So these discs was transferred from the space segment, like the carbon ceramic material used in those nozzles, into a braking system. So this is, for example, transfer of technology. So we are using space material into some automotive area. What about the eye? If we look into this picture, we can see pretty sharp image of an eye, I think. What is it? How is it related to space technology or technology transfer? Well, there was a mission, Darwin, I think, and it was about looking for habitable planets. It wasn't really. It wasn't like finished. It was just a case study or something like that. But the satellite has to withstand or damp any vibration generated on the satellite. So there was a damper that was developed specifically, not for this one, but for the Darwin satellite. And if you have this eye and you have to like make a surgical some surgeries on this, like you have to put it in another how is it? The black circle. any word for it? Oh, sorry. Yeah. Okay. So if you have to remove it or replace it, you have to use a very precise surgical equipment. So vibration is the main reason that can make it a mess. So this damper from the satellite was used in this like a microscope which is hanging from the ceiling, and it dampens the vibrations that are generated in this room. So this is a medical surgical equipment located in Netherlands, in the University in Netherlands. And it is basically for eye surgeries. So it has a damper from space technology. This is also transfer of technology. Another examples, we have a moon landing system which is transferred to autonomous drones used on Earth. So you can use some technology that was created for very precise landing on another planet or moon to put it on some drones autonomous. Or you can use another materials like in the Airbus rocket or Ariane 5 or 6. There is this this shell protection of satellites. And they were transferring it into the Airbus planes to withstand the temperatures or it was also very light, so there is also the demand for lightening the whole structure. Another possibility, if you are astronaut, you are monitored all the time. So there is some medical monitoring for astronauts that were transferred to pregnant women to obtain some information about the baby. Or if you have some deployable mechanisms in space, you can use it to create this device, which is basically a container with filled solar panels that are moved to one place, and they are like expanded, and a new solar plant are created like in a minute. Or there is something like a spectroscope technology used on satellites that are transferred to a very dumber device, washing machine, not washing machine, sorry. What is it? Yeah, it's washing machine. Yeah, okay. This laundry machine, I think. Okay, so it's basically looks for the colors of the shirts, etc., and it can tells you what temperature should be applied, or something like that. So all of those applications were transfer of technology from some space segment to terrestrial applications. And just a quick word about the philosophy of technology, or the transfer, innovation, etc. So what is a technology? Technology is basically anything that is created by science that is put into the human life and created somehow. So we can change by the technology the environment around us somehow. If we transfer the technology, then what are we transferring? You could see that we didn't transfer all the satellite into some another applications like this laundry machine, but we transferred only, for example, the know-how, how to do something, or we transferred the physical form of the know-how of the device, or we are transferring only the legal rights to acquire the technology and to exploit it. And one last question is technology and transfer innovation. Well, innovation can be described as a new combination, according to Schumpeter, sorry. And it's basically if you put something that is already made and put it into another thing, then you can get a new combination that is, for example, better, and it can lead to another innovation, etc. It is also perceived by a customer or some services or society. So it's more about the marketing of the thing. Yeah. How it is connected to this, what I'm showing it to you. This is a satellite picture of New York City, and there is some data from satellite. For example, this light pollution from night, and some company look on this data and say, hey, we can use it. For example, if I'll be Italian and I would like to start a new restaurant in New York, then I would probably go to those places where are a lot of street lights, because there is life at night and I want to make money. So they are using those data and they are transferring it into the information that are provided to customer. So basically, if you are for example, if you have construction sites, something new is developed in some locations, the construction sites are always like light up because they are working also at night, during night. So all those things are collected by this company, and they are provided in a way for some customers. For example, I want to build up some building for accommodation. Which location is best for me to provide it to the customers? Where are the customers for me? Or if I have a restaurant, I want to build a restaurant. What is the best location in the city that I should apply for? How to transfer technology into business? Basically, there are two opportunities. You are already a big company. For example, Ferrari, you get a license from NASA that you can use their material to build the brakes, or you can choose some, for example, patents. You pay for them somehow, and you start a new company and be an entrepreneur. What is entrepreneurship? Like if you are starting a new company, you are entrepreneur of this company. It's basically it's the activity of setting up a business or businesses that are taking on financial risks in the hope of profit. There are some definitions or some possibilities of preferable assets of those entrepreneurs. Like they have to be self-motivated, they have to have high energy, self-confidence, etc. But there is no definition of it at all, because no one tells you you are best person to be an entrepreneur of some space company or any company. There is no one for it. You have to just do it. So you have to try it. If you try and fail, it is the best, not the best way, but failure is also a process of learning. This is also some really good story about the picks and shovels. It is basically during the gold rush. There was a group of people that was mining gold, and they went there, started to mining gold that they wanted to sell after, but they didn't have shovels, or they have limited amount of shovels. And to dig up a gold, it has to be a lot of equipment for it. So a new company or some provider of those shovels says that, okay, I can provide you with those shovels. And they set up a new business and they deliver them the equipment for it. And eventually they make more money from it than those gold rushers, because they have to dig up the gold, pay for the shovels, and they have a stable business. So this is a really good story, not to focus only on the shiny things, but also for the maintenance of those things, because there is a real business in it. Where do entrepreneurs come from? There are basically three categories of entrepreneurs. We are lonely or a lonesome cowboy, or you are a spin-off, or you are incubee. Lonesome cowboys, they are basically persons or group of people that had nothing to start with. They had no support or strategic network or mentorship or something like that. It's basically a cold start because you have no experience, no money, and you are very self-motivated in this. So this is not the good choice how to start something. The best choice is those two. You can spin off somehow. You have, for example, a mother company or university, and you have really good idea how to monetize something. Then you can start a spin-off of it. There are advantages and disadvantages of it. The advantages, the mother company keeps you with money, some mentorship, collaboration. You have some projects with it, so it's good. But also, they own some legal rights to your product. So it could lead to a poor innovation and also slow down the process. And there is a third one, the incubates, which we'll be speaking about. Sorry, this is a Czech spelling. It's basically babies that are out of an incubator, and they are working with possible investors into them. They are speaking with them. They are their mentors. And the best of it is that the incubates should not have any experience with the business and so on, and the incubator can provide you with some reputation also. Why ESA loves entrepreneurs? Because the entrepreneur has to move really fast. Because if you start something, there is a lot of people or a lot of companies that are faster than you, because they have money, they have some experience, they have knowledge, they have people. So you have to move really fast, or you'll be slower down than the cheetah. You have to also adapt to a situation. There is a COVID pandemic or something like that. You have to adapt for it. If you do not adapt, you will die. You have to be fighter, because you have a team of people that are dependent on you. If you fail them, you fail also yourself. And the last part, they are basically the best people that can do anything from nothing. So with minimum viable product, they can provide you with something that is functional. And it all stands on the middle segment, which is team, because there is nothing like you are entrepreneur and you are the company. The people are the company. Your team is the company. So you have to care for them. How ESA supports, or what is the approach of ESA to commercialization? Basically, they look up for talented people. They speed up or kick their start by providing them with money, with some capital, and also some mentorship or some knowledge. There are several possibilities how to obtain money from ESA or support from ESA. Either you are a big company that has also already some matured technology that you can sell, then you can use the investments of ESA by business support, or they can market your product on their marketplace. Or if you are starting something new, then you can use, for example, the PhiLabNet or ESA big network, which is basically the incubator for the starting companies. Or you can connect with the ESA brokers that are connected to other big technology groups, big projects, and they can provide you with more information in it. We'll be more speaking about the business incubation. What is it exactly? It started in 2000 in the Lisbon Promise, where the former set of countries decided that they will support their own companies inside their state. And for us, it all started in 2008 by a signature of our Prime Minister, Mr. Topolánek, that Czech Republic entered the European Space Agency. Since then, we can do things in space. ESA Business Incubation Center is all around the ESA member states. It is 29 incubation centers. In Czech Republic, we have 2 of them, one in Prague, the second one in Brno. Around 240 startups are selected annually for incubation. They are provided with money, with support, and there are already over the 1,600 supported startups overall. 5 main problems when starting a business. The first one is the product or service. you are basically too long focused on perfection. Okay, I'll be ending very soon. Sorry. Product or service, you are too focused on your product. You have to do it precisely, good, etc. So you have to learn how to kill your baby, for example. Not exactly, but if you have a product that is no perspective, you have to move it and focus on something new. So you have to know your customer, what the customer wants, because you are doing business to support your customers. The second one is the finance. You are lack of financial skills. You don't have any finances. You have to find an investor and so on. The cash is here, the king. So you have to have a cash, or there is a bigger company that can buy you or do something greater. The third one is the sales and marketing. You underestimated the sales effort or the market at all. No sales mean no cash, no company. You can say goodbye. The fourth one, is the team. As I said, the team is the main vital thing for your company. If you do not have people that are motivated and want to do anything for you in your team, then you can find another people because they can drag you down. And the fifth one is the business model. You have to do a business model prior to starting your company. You have to do business canvas, know your customers, find the financial sources, etc. And this was also what we done at our workshop. So this is Philip doing his business canvas. We had some product that we want to sell to a customer, so we have to find our customers. We have to think of what the customers want, and then provide them with some solutions and so on. This is me. And just very quick few words about the ESSA BIC, because some of you may be interested in it. It supports startups with maximum of 5 years since the establishment. Your company has to be space related, so you either use the space data or you are making something that is space related. The incubation centers are in Prague and Brno. It is open for also students, but if you have some great idea, you can get in contact with them. They provide you with some mentorship, or they can just say, oh, forget it, do something new. They can provide you with a 2 years incubation with up to 50,000 euros, with possibly more investments from the investors and venture capital. And the benefits are that you have some reputation, that you are ESSA incubed, you are visible to the market, and it is something. The application, forget it, the application are open, I think, twice a year, so there's, I think, in March and in November, so you can prepare something. And it's basically pretty simple. You have some pre-mentoring, then you can create a business plan, the think of your business, get the application, do some format check, some pitch talk before the investors, and then you can sign a contract with them if they are happy. This is just some data of it. If you are interested in the companies that were supported in Czech Republic, you can visit the ESSA BIC, Czech Republic, and get to know with them, get more information about them. One or two last slides from great minds about the entrepreneurship. If something is important enough, you should try it, even if it is probably if it will be probably some failure or something like that, because the failure is the main teacher for us. I can remember any failure that I did in my life, and I learned a lot of it. And the second one is do or do not. There is no try, as Master Yoda said. So yeah, this is pretty much of it. If you have any questions about the ESA transfer of technology, you can ask me. If you have any questions about the ESA co-founding, we can talk after this. So thank you.
So sorry, it's me again. When you mentioned the salaries for the internships for the PhD students, you mentioned it's between 2,300 to 2,700. Is it with costs included for the living, or is the living provided by ESA?
No. As I have the information from my colleague, then this salary is basically, if you have a job, you get this salary and you can find your own accommodation. So it's why I said it's not so much, because if you are living somewhere else, in Netherlands, for example, then your wages are way too high, so you don't get a lot of from it. Yeah, thank you.
Okay, so today was a little bit exceptional for Space Beer. We have like 3 presentations, and we are really glad you stayed with us, and really thanks to our guests that they had their presentation. So thank you very much. Yeah. Now I want to say about this action here in Kachnička about Movember. You still can buy the beers and support the good cause, and still you can give some donations on that occasion. So, yeah, for me that's all. Really, thank you that you stayed with us, and see you in 2 weeks on the next Space Beer.